Hello there, Mr. Sutton here, bringing you the AB Calculus 6-6 Extra Practice Number 2 solutions on motion and position. On this problem, we have the acceleration of an object given by this a of t function. We want to know the net change in velocity from time 0.75 to time 2.25. Well, to find the net change in velocity, we just need to take the integral of the derivative of velocity, which is to say the integral of acceleration, along this time interval from 0.75 to 2.25. So let's just go ahead and plug this into the calculator now. So here I am on the calculator. I've entered my a of t function in the y1 of my y equals. Let me just quit out of there now, and I'll do math 9 to pull up my integral. I'm going from 0.75 to 2.25, and let me just pull up my function, alpha trace y1. So there's a of t that I'm taking the integral of on the calculator. We've got dx, and just press enter. Comes out to about 0.984 if we round that off, which is going to give us answer choice D. For this problem, we have a particle going along a straight line such that its acceleration is given by this 12t function, and they're telling us at time 0 we have a velocity of 2 and a position of 5. Based off that, we want the expression for the position of our particle for time greater than or equal to 0. All right, so for this I'm starting at acceleration and I have to get back to position. So that's going to involve basically solving two differential equations. One we're going to solve to get to velocity, and then once we have velocity we're going to solve that for its particular solution to get to position. So starting with a of t equals 12, I'm going to take the antiderivative of this, which is going to be antiderivative of acceleration is velocity. So we have v of t equals, reverse power rule here. This bumps up to a 2. So we have, dividing by that, we have 6t squared plus c. And I'm going to call it c1 because I'm going to have a few constants in this problem. So this is going to help me get my velocity function, which I can then turn around and use to get my acceleration function, or my position function. So to find out c1, which we need for this, we have to take the velocity at time 0, or whatever time they gave us. They did give us time 0. They said the velocity was 2. So for v of t, I can write 2, and that's going to equal 6 times 0 squared plus c1. Well, 6 0 squared is just 0, so we have that mystery constant has a value of 2. So that means we have 6t squared plus 2 for our velocity. At this point, we're going to take the antiderivative of this expression and figure out the position function. So antiderivative of velocity, so that's going to be position, which I'll call s of t. That's kind of the standard variable for position. And that's going to equal, let's see, this bumps up to a 3 for the exponent. Dividing by that, we have 2t cubed plus 2 times t. Plus, don't forget, we have another constant. I'll call this one c2. And now I need to get the value of c2 in order to get a full expression. Now, just kind of looking at my my answer choices, I mean, you can see we've already got 2t cubed plus 2t plus something. There's only one answer choice that matches that format. So it's a pretty sure bet that D is the answer choice. But just to finish this thing off, if I plug in 0 for time, I should get back a position of 5. So I can write 5 equals, well, all this stuff with 0 plugged in for t. Pretty much everything gets zeroed out except for the c2 over there. So we have c2 equals 5, which means we can rewrite this now as 2t cubed plus 2t plus, big surprise, 5. And that does indeed give us answer choice D. For this problem, for time greater than or equal to 0, the acceleration of an object going in a straight line is given by this a of t function. We want the net change in velocity from time 1 to 5. So to get the net change in velocity, I need to take the integral of the derivative of velocity. Well, the derivative of velocity is just the acceleration. So I basically need the integral from 1 to 5 of a of t dt. And let me just plug that in my calculator because this is a calculator problem. So here I am in my calculator in the y equals. This is the a of t function that I've plugged into my y1. Quitting out of there now, let me just do math 9, and I have the integral from 1 to 5. So 1 to 5, we'll do alpha trace y1, that's where I stored my a of t function, dx, press enter, and that's going to come out to about 16.868. That is our net change in velocity, so that's choice D. For this calculator-based free response problem, we have a test plane flying in a straight line with a positive velocity, and we're doing this in miles per minute. And v is differentiable. Selected values of that function v from 0 to 40 are shown in this table. First task is to use a midpoint Riemann sum for subintervals of equal length, values from the table to approximate integral from 0 to 40 of v of t. And then they want us to, using correct units, explain what all that means. Okay, so let's get our midpoint Riemann sum with our integral first. Since I have 4 subintervals of equal length and I'm going from 0 to 40, well, splitting that up 4 ways, that means each interval has to have 10 as its width. So I'm going to set this up as a series of base times height sort of rectangle areas. First, I'm going to write integral from 0 to 40 of v of t dt is approximately equal to. I need to write approximately equals because I am approximating here. This is not the exact value of this integral, and I need to let people know that I'm aware of this. So now I have a bunch of base times heights going on. My base in all of these cases is going to be 10. So the first rectangle, I'm going to have a base of 10 from 0 to 10 times a height of, and now since this is a midpoint Riemann sum, MRAM, I have to use the middle value, the height at the middle x value or middle input value for this rectangle. So that height is going to be this 9.2 in the middle here. So I have 10 times 9.2 plus, next I have a base of 10 times a height of 7, again using the middle value. After that we have 10 times 2.4, and finally 10 times 4.3. Now you could leave it like this and stick units on the end. It is a calculator problem, so I'm just going to crunch these numbers right now. To make this a little faster on the calculator, since all of these things have factors of 10, I just basically factored the 10 out and added up all the stuff that 10 was being multiplied by. So that comes out to 229. And since the original was in miles per minute, integrating that basically multiplies it by a time unit, canceling out the minutes. So that just leaves us with 229 miles, which kind of makes sense. I mean, if you're trying to figure out the total change, given this rate of change of velocity, that the total change is going to be in miles. So what does this mean? This means that from 0 to 40 minutes, so we need a time unit in here, from 0 to 40 minutes, our plane is flying a total of 229 miles. For this part of the problem, based on values in the table, what's the smallest number of instances at which the acceleration of the plane could equal 0 on the interval 0 to 40? So just to be clear here, when we talk about acceleration, we are talking about the derivative of velocity, v prime, and we're talking about the instantaneous rate of change in velocity, which we don't have anything to really tell us. One thing we could get at, though, is if we could at least find the average rate of change of velocity. Since this is a differentiable function, since v is differentiable, that means the mean value theorem does apply here. So I can at least figure out what, if I'm given an interval and I know the endpoints, I can use those to figure out at least one possible instantaneous rate of change for velocity over that interval. So now I'm not interested in just any old instantaneous rate of change for velocity. I want to find the smallest number of instances when the acceleration, which is the IROC of velocity, is 0. So I'm specifically looking for intervals that when I do the average rate of change on them, I'm going to get back a value of 0. And then I'll be able to use the mean value theorem to prove that we're guaranteed that v prime equals 0 somewhere on those intervals. So I'm going to be very selective in which intervals I look at here. I'm going to look for intervals. In order to get 0 with average rate of change, I need the output, the v value, to be the same at both endpoints of my interval. So looking at my table, this first value here, we've got 7. Does that get repeated anywhere? It does, here at time 15. So I'm going to set up an average rate of change from 0 to 15. So the AROC then, on 0 to 15, we're going to have 7 minus 7 over 15 minus 0. And I do need to show all this in order to prove anything. So that comes out to 0 over 15, which is just 0. Therefore, since we have this differentiability, the MVT guarantees that v prime, which is the acceleration here, equals 0 somewhere on the open interval from 0 to 15. So that guarantees there's at least one place we have an acceleration of 0. Are there more? Well, we have to keep looking now for velocity values that get duplicated in this table. So 9.2 doesn't get duplicated anywhere. 9.5, same deal, doesn't get duplicated anywhere. How about 4.5? No such luck. How about 2.4? Well, yeah, the very next one is 2.4. And if you keep looking, that's the last value that gets duplicated anywhere. So it's really down to 2.4. Now, so we're going to do the average rate of change just like we did here, except this time we're going to go from 25 to 30. So average rate of change there, we have 2.4 minus 2.4 over 30 minus 25. Comes out to 0, just like the other average rate of change, which guarantees by the MVT, mean value theorem, that V prime is 0 somewhere on 25 to 30. So overall then, we're guaranteed that V prime, also known as acceleration, is going to be 0 at least 2 places on the open interval from 0 to 40. For this next part of the problem, we have a function f defined as this crazy trigonometric monstrosity, and this is used to model the velocity of the plane from 0 to 40. Okay, so according to this model, what is the acceleration of our plane at time 23? So to find acceleration, since the velocity is given by f, we just need to do f prime of 23, and that'll give us the acceleration. So we're just going to do that on the calculator. We actually don't have to show anything else beyond what we've shown here and the answer, because we're just taking the derivative at a specific spot. So I don't even need to tell people what f prime looks like algebraically. I just need to say, hey, I'm about to find f prime of 23, and then go ahead and do it. So here I am on the y equals of my calculator. I've entered f of t as my y1. Quitting out of there now, I'm just going to take the derivative, so math 8 of, let's see, put an x down there, and now I'll do alpha trace y1. So I'm doing math 8 derivative of f of t, and then I'm going to use an x value here of 23, because that's what I wanted to plug in. We're doing f prime of 23, and that's going to come out to about negative 0.408. And what are the units going to be on this one? Well, since I'm taking the derivative of velocity, every time I take the derivative with respect to time, I divide by time. So this is going to be miles per minute, or miles per minute squared. For this last part of the problem, using the model F from part C, we want to know the average velocity of the plane in miles per minute over 0 to 40 minutes. Okay, so I've already got the f function. I'm just going to set up an average value kind of integral here. So I'm going to have 1 over the interval length, that's 1 over 40 minus 0, or 1 over 40, times the integral from 0 to 40 of the thing I'm trying to average. I'm trying to average velocity, which is the f function from part C. So I'm just going to put f of t dt in here. And there's nothing else I actually need to show in terms of work. I just need to do this on the calculator now. So just to review from part C, here's the calculator, here's my y equals. In part C, I plugged my f function into the y equals. It was this 6 plus cosine of, it was t over 10, plus we had 3 sine of, I believe it was, 7t over 40. So I've already got that in the calculator. I'm just going to escape out of there now. And I'm going to do 1 over 40, so fancy fraction, alpha y equals 1 over 40. So to get my fraction there. Now I'm going to do integral, so math 9. And we're going from 0 to 40. And I'll do alpha trace y1 in there and a dx. So if I do this on the calculator, this should give me my integral. Press enter. And that comes out to about 5.916. And that was average velocity, so that's miles per minute. And we are done. On this no calculator free response problem, we have a train A running back and forth on an east-west section of railroad track, and A's velocity given in meters per minute is given by the differentiable function VA of t. We've got some values for VA of t in this table above here that might be helpful. So our first priority here, our first task, is to find the average acceleration of train A on the interval from 2 to 8. Well, if I want average acceleration, that means I'm trying to find the average rate of change of velocity. So I just need to use AROC on this velocity function over the interval from 2 to 8. So basically VA of 8 minus VA of 2 over 8 minus 2. This is our general setup here. VA of 8, that's going to be negative 120. Of 2 is going to be 100, so we have negative 120 minus 100, all over 8 minus 2. And you could just leave it like this and put units on it, or you could reduce it. This is negative 220 over 6, which is negative 110 over 3, and that's going to be in meters per minute squared. For this part of the problem, they're asking if the data in the table support the conclusion that train A's velocity is negative 100 meters per minute sometime between times 5 and 8. Give a reason for the answer. Okay, so if we're asking if a function gives us a certain value, one good theorem to use on this situation is the intermediate value theorem. Now, in order to use this, we need to show that the function is continuous and that the value we're looking for, negative 100, is sandwiched between two values in the original function. So let's talk about the continuity piece of it. They said that v of a was differentiable. Well, if velocity is differentiable, then by definition it is also continuous. So this gives us the continuity piece we need to use the intermediate value theorem. We also need to show negative 100 is between the beginning and the ending output values on this interval from 5 to 8. So let's take a look at the values of 5 to 8. We see that v of 8 here, VA of 8, is negative 120, and 5 is the other one. V of 5 is 40. Now the key here is that negative 100, the value we're looking for, is actually between negative 120 and 40. Since this is a continuous function, there's no way to get from negative 120 to 40 without also going through negative 100. Therefore, by the intermediate value theorem, VA of t has to equal 100, negative 100 I should say, somewhere on the interval from 5 to 8. For this part, we're told at time 2, train A's position is 300 meters east of origin station. That's a cool name for a station. And our train's moving east. We want an expression with an integral that gives the position of A in meters from origin station at time 12. So that's the first part of this question. We'll deal with the rest of it later. So first, we need to figure out where we are. Now, they told us at time 2 we were at 300. We have the position at a certain time. We also have a function for the rate of change of position, the velocity. So what we're going to do is use our fundamental theorem to write this expression. I'm going to say that our position at time 12 is going to equal 300. That's our position at time 2, plus the integral from 2 to 12 of this VA of t function. Don't forget the dt. So this is the expression that gives us the position at time 12. To actually find that position, though, that's the next part of this problem. We don't actually have a formula for velocity, but we can estimate it, and they're asking us to estimate it using a trapezoidal sum with 3 subintervals in this table. Okay, so let's set this up. I'm going to say that this is approximately equal to the following. So we've got the 300 east that we're starting with, and to that I'm now going to add 3 trapezoids. So I'm going from 2 to 12. That's 1, 2, 3 subintervals with trapezoids. Each of these is going to be a base 1 plus base 2 over 2 times height kind of situation. So for our first trapezoid, we have the bases of 100 plus 40 divided by 2 times a height of 3. The height's just going to be the distance in between the times here. So that's our first trapezoid. For the next one, we're going to have 40 plus negative 120 over 2 times a height of 3. And finally, we're going to be adding negative 120 plus negative 150 over 2 times a height of, let's see, 8 to 12 is 4. So it's a little different than the first 2 trapezoids. And if I wanted to, I could put some units on this. This would be meters. And then I could just call it a day. But I'm going to simplify it to see just where we are, because I'm kind of curious. So 300 is just itself. But this stuff, now let's simplify it a little bit. So we have 100 plus 40 is 140. Divided by 2 is 70. 70 times 3 gives us 210. And for this next one, this is going to be negative 80 over 2, so negative 40 times 3 is negative 120. And finally here, we have a 4 over a 2 here that we can cancel. So this is going to be negative 270 times 2, which is going to be, well, that's a big number. Let's see, negative 450. There we go. So going from left to right, we've got 510 minus 120 is going to be 390, minus another 450 is going to be negative 150 meters, which I could also call 150 meters west of origin station. For the final boss battle on this free response, we have a second train. There's always a second train, train B, traveling north from origin station. And at time t, velocity of train B is given by this VB of t function here that looks quadratic in nature. And they're telling us at time 2 the train is 400 meters north. We want to find the rate in meters per minute at which the distance between trains A and B is changing at time 2. So this is a little more complex. I'm going to draw a picture to help me out with this. So we've got origin station, we've got train B going north, train A is going east, and this is a triangle then that's going on here. So here is train A going east, train B going north, and we see that the distance between these two trains at any given time is basically the hypotenuse of a right triangle. And my task in this problem is pretty much to find the rate at which this hypotenuse is changing, the rate at which this distance is changing. So to do that, I need to be able to talk about the different quantities in this triangle. I'm going to label these sides as x for the left-right. Y is going to, I guess this is the east-west actually. Y is going to be the north-south, the distance from origin station north, and then z, that'll be the distance between the two trains. So in order to, since I have multiple rates of change going on, I'm asking for the rate of change of z, and I know a little bit about the velocities, the rates of change of x and y. That means that I have a related rates kind of situation. So I need to start with a formula that ties all of these rates of change together, and then take the derivative of everything with respect to time. So implicitly differentiate, as it were. Well, the formula that ties all of these distances together is going to be the Pythagorean theorem, x squared plus y squared equals z squared in this case. So now I'm going to take the derivative of all of this with respect to time. So derivative of x squared, that's going to be 2x times dx over dt. Every single one of these letters is a function of time, so we use the chain rule every single time and multiply it by the derivative of the distance function with respect to time. So this next one then is going to be plus 2y dy over dt, and that's all going to equal 2z times dz over dt. So again, what I'm looking for in all of this is the rate of change of this hypotenuse. That's going to be this dz over dt quantity. Well, that means I've got a little bit of a task ahead of me because I have to find all 5 other unknowns in order to figure out dz over dt. So let's go through and see how many that we can come up with. X, that's just the distance between origin station and train A at time 2. This is all happening, by the way, at time 2. So at time 2 here, it looks like, let's see here. Ah, yes, here it is. I just flipped back to part C here. In part C, they actually told us that at time 2, train A's position was 300 meters east of origin station. All right, so that gives us what we need for that. So here I am back on part D. We found that x at time 2 has a value of 300, so I've got 2 times 300. Now how about dx over dt? Well, that's how fast the train is going, or at least the velocity of train A at time 2. We can actually look that up in the table. When we plug 2 into our table, we get back a value of 100 meters per minute. So that's 100 right there. How about the y value? That's how far train B is at time 2. Well, they actually told us that in part D. They said at time 2, the train B is 400 meters north. So we've got 2 times 400 there then. dy over dt, that's going to be a little bit more work. That's how the velocity of train B at time 2. To find that, we need to use this velocity function they gave us for train B. So basically, dy over dt is going to be vb of 2, which is all of this stuff with 2 plugged into it. So let's do this out now. This is going to be, let's see here, 4 times negative 5, that's negative 20, plus 120 is going to be 100, plus 25 is 125. So this is going to be 125 that we're multiplying there. We're getting there. We just have one more thing that we don't know, and that's the value of z. That's this distance here. Now the good news is that this is really just a distance in the Pythagorean theorem. So if we just take the square root of both sides of this Pythagorean theorem, we can figure out the distance of side z. So that's going to be the square root of 300 squared plus 400 squared. And you might recognize that this is a 3, 4, 5 triangle, right triangle, in which case you wouldn't really need to do any number crunching to know that this comes out to 500. But you could do the number crunching. This is 90,000 plus 160,000. That's 250,000, whose square root is 500. Anywho, we've got all of this equaling 2 times 500 dz over dt. And at this point, we just have to solve for dz over dt. Now, you could play it safe and just divide everything on the left by the 2 times 500, but I feel like simplifying this just a little bit. So on the left side here, this is going to be, let's see here, 600 times 100 is 60,000. And here we have, well, let me just do these in a different order here. Let me do 2 times 125. That's pretty easy. That's 250. Times 400, let's see, 4 times 25 would be 100. Throw in 3 more zeros, we've got 100,000. And then over here, this is 1,000 dz over dt. So if I add these together, that's 160,000. Dividing that by 1,000, I just have a dz over dt value of 160. And we should probably put the units in there. Now, what are the units going to be? Well, z had units of, this was minutes, or meters rather. Z was in units of meters. Time was in minutes, so this is meters per minute, and that is the rate at which the distance between the trains is changing at time 2.